Okay, so in yesterday's class, we discussed about experimental study of photoelectric effect. In experimental study of photoelectric effect, there are four different graphs. Is it not? Four graphs. What is that? The first graph was intensity of light versus photo current or photoelectric current. Intensity of light versus photo current or photoelectric current. So in this one, as the intensity of light increases, photocurrent also increases. Is it not? As the intensity of light increases, photoelectric current also increases. This is the first one. The second graph is a plate potential versus or collector plate potential versus photocurrent. So what happens as the okay, I'll draw the graph also, but okay, I'll just use one side of the graph. Okay, this one. So now, so here he says the first graph. See, the first graph is in this way. Okay, this is intensity of light versus photocurrent. Intensity of light versus photocurrent. So what happens? As the intensity of light increases, the photocurrent also increases. But the condition is first it depends on frequency of light. So if for a particular frequency, if the electrons start coming out, then what happens? Photocurrent also, as the intensity increases, photocurrent also increases. The second graph is like this. This is a plate potential, collector plate potential. Okay, collector plate potential versus photocurrent. Okay, collector plate potential versus photocurrent. These four graphs are very, very important. Okay, so what happens here? We can see here, this is the graph. So when it is zero, when the collector plate, so what we are doing now, the plate potential. Good morning, Arjun. So think that the plate potential was plus 5 volts. Okay, now we have started reducing the potential like plus 3, plus 2, plus 1 and 0, then minus 1 like that. So what happens at a particular negative? Even though it is 0, it will be still receiving the electrons. It doesn't mean that it will stop receiving the electrons. The collector plate still receives the electrons. Now, what happens if you start making it negative? It starts like at a particular point, it will become 0. This is said to be minus V0. Is that clear? That minus V0 is known as what? Minus V0
stopping potential.
Stopping potential. Very good. What is the definition of stopping potential? What is the definition of stopping potential? The minimum voltage or the minimum potential of anode for which no photoelectrons are received. Okay, the minimum so the minimum potential of anode for which no photocurrent is no electrons are received by the anode is known as stopping potential. Then what is photoelectric effect definition? What is? Can anyone define?
Sir, photoelectric effect.
Definition.
Photoelectric effect is like when light of given frequency is incident on a metallic surface, then electrons are ejected one by one. This phenomenon is known as photoelectric effect.
Very good. When light of certain frequency incidents on a metallic surface, so then electron starts emitting or ejecting outside. This phenomena is known as photoelectric effect, and the surface used for this purpose is known as the surface
used for this surface is known as photosensitive surface.
Photosensitive surface. Yeah, the surface which is used for this purpose is known as photosensitive surface. Okay. Third one, photosensitive surface, and the electrons which are coming out of the surface is known as photoelectrons. Okay, is that clear? And the current which is flowing through the circuit due to photoelectrons is known as photocurrent. Now, yes, next one is what? Threshold frequency. What is threshold frequency? What is threshold frequency? Threshold frequency means it is
minimum frequency for which electron emission takes place.
Yeah, it is a frequency of. Okay, it is a frequency of incident radiation for which electron starts coming out or emitting out of the surface photosensitive surface is known as stopping potential. Okay, so we have total 4 definitions. Number 1, photoelectric effect. Number 2, work function. What is work function? Work function.
That is that minimum energy required for electron to be knocked out, no?
Very good. The minimum energy of the minimum energy to bring the electron to the surface of the metal. The minimum energy to bring the electron to the surface of the metal is known as work function. Okay, generally it is measured in electron volts. Okay, 1 electron volt is equal to how many joules?
1.6 into 10 raised to minus 19 joules.
Very good. 1.6 into 10 to the power of minus 19 joules. This is the energy. Okay. Now, so these are the 4 definitions, 4 graphs. First graph, second graph we have done. So what happens at this is meeting at a particular point. So suppose if I take more intensity, like suppose this is I1. Now, suppose if I increase the intensity, so what happens? Again, it meets at this same point. Again, if I increase the intensity, it meets at the same point. So that means what if even though for a particular color, I'm not changing the color of light, means frequency of light. Think that it is a yellow color light. So I have just increased the brightness. I3 is greater than I2 is greater than I1 for one particular color light, for one frequency, one color or one frequency light. What happens? What happens? The stopping potential remains in, that won't change. So that is about the second graph. Okay, third graph. What is the third graph says? So first graph is photocurrent versus current, intensity of light versus photocurrent. Second one is collector plate potential versus photocurrent. And these potential, there are 3 names for this. What are they? The first one is what? Stopping potential or retarding potential or cutoff potential. There are 3 names for this. Once again, stopping potential or cutoff potential or retarding potential. Okay. Now, the third one is same graph, but what we are doing is we are changing the color of the light now with the same intensity. In this graph, it was like frequency was same. Now, frequency is not same. Only intensity of light is same. Now, suppose see here, this is for new one. Okay. And this is saturation current, maximum is, even though if you increase the brightness of the light, this is for saturation current. Now, see, now this is meeting at new 2. This is meeting at new 3. Okay, this is new 3, and this is V01 minus V01 minus V02 and minus V03. Okay, these are all the 3 stopping potentials for different frequencies. Where new 3 is greater than, new 2 is greater than new 1. Maybe new 1 is yellow color light, new 2 is green color light, new 3 is maybe blue color light. We have taken. I am only taking color light only because I can understand. If students can understand easily the difference of the colors, because of the frequency and all. Otherwise, it is difficult to explain in infrared region and UV region. That is only intention behind it. Is that clear? This third graph.
Yes,
sir.
Yeah. Now the last graph. What he says, the last graph is about the fourth graph. If you look at the fourth graph, it is like this. This is stopping potential versus frequency. Okay, frequency. This is new 0 and this is new 0 dash. Okay, so these are the cutoff. This is threshold frequencies. So what happens? Suppose I have taken 4 color lights. Like this is blue, then green, then okay with GR, right? So when I say with GR, violet, green, I will take indigo or a violet. Okay, I will take here violet, then blue, then green, and this is yellow. Example. So maybe yellow is a starting point. As the frequency is increasing, stopping potential is also increasing. You have seen that in the last graph. As the frequency is increasing, stopping potential is also increasing. Is it not? In the previous graph, you have seen that for different frequencies, for the same intensity of light, for different frequencies, stopping potential is different. Now maybe for this it is green here, green, then blue, then violet. Maybe it is like this. Okay, it is in the different way. Are you understanding? Yes. So from
Yes, sir.
this graph has played an important role. Okay, that I'll explain. See, suppose this is what is this called? This point. See, what is this called?
That is stopping free. This thing.
No,
Stopping
I have just extended this line and it is meeting on y-axis. What is this point called?
Y-intercept.
Y-intercept. Very good. It is so from this particular graph, we found out the Planck's constant actually. That is the significance of this graph. Planck's constant means see, we have the equation of line, right? Y is equal to mx plus c. Is it not? Y is equal to mx plus c. Using this, so we have the Albert Einstein equation. In that, while solving that equation, I will explain that. Okay, is that clear? Now,
Yes, sir.
okay. Before okay. Now 3 topics are remaining. One is what is that for Einstein's that is he supported the particle nature of light. So that we have to discuss. That is particle nature of light, the photon. And second is about photoelectric equation that we will discuss. And third one is de Broglie wavelength. Okay. So I'll start with de Broglie. So already it is done there on the board. So so this man, you know, Louis Victor de Broglie, Louis. So see, actually the topic name, dual nature of matter and radiation. So actually, de Broglie, he was doing research on, dual nature of matter and radiation, the same topic, the name of the lesson. He was doing his thesis, or the topic was dual nature of matter and radiation. There are 2 groups of scientists. One group of scientists, they supported particle nature and they proved it experimentally. Who? Newton, Max Planck, and Einstein. They told that light travels in the form of particles. The second group of, and they proved it experimentally. The second group of scientists is who supported wave nature of light. So they support it was supported by Huygens and Young. Okay, Thomas Young. So Huygens gave the concept of wavefront, and then Thomas Young he gave the explanation of interference of light using wave concept, like that. There are so many scientists, not only these 3. There are so many scientists here in both the particle nature and wave nature. There are so many scientists who supported particle. Some supported particle nature, some supported the wave nature, and they did it experimentally. Now, what was he doing? De Broglie, this man, he wrote a thesis like dual nature, means both matter and radiation. Actually, there are 2 types of research. One is theoretical research, one is practical research, means applicative research, what we say. Theoretical research is very difficult actually. The problem is, you have to gather the literature and you have to study through the literature. Formulation mostly. You have to write the formulas and you have to explain all the formulas. It's very difficult. Whereas applicative research means only just you take the research what was done by theoretical researchers and put it into practice. That's it. Okay, mine was theoretical mostly, theoretical research, and then later I put it at last in the programming and all. So which was very difficult. So I started my literature gatheration from 1850. You can understand now, around 150 years old research we have to, like, I started from there, from the starting point. My starting point was there. So in the research we have to do this lot of work. So what Louis de Broglie, when he wrote the thesis and he submitted to the professors, then actually the professors wanted to reject this concept because there was no experimental evidence for that. So, but when you in research, whenever you want to accept it or you want to reject it, there should be a proper strong reason for that. Okay, you cannot say like that. Okay, it's not possible. You cannot just reject like that. It has to go to proper channel. Then they wrote a letter to Albert Einstein. Albert Einstein was in London. Actually, Albert Einstein was born in Germany. Then he went to London. Then he went to US after that. He took the nationality of US after later on. So he was in London at that time. Then they wrote a letter to give a reason so that they can reject the thesis. At that time, he told Albert Einstein told, okay, you send me the thesis. I want to see the thesis means the book what we combine. Then when they wrote the when he saw the thesis, then he said that Albert Einstein told, if we reject the thesis of de Broglie, then we are and tomorrow if he proves it is correct, then we all will become fool. So let him award the thesis, award PhD. So he was awarded PhD in 1924 on the same topic. He got the Nobel Prize in 1924. Okay, for finding the dual nature of matter and radiation. How it was supported actually? This was supported when he published the paper at the same time. Davischer and Germer, 2 scientists, they started publishing the papers on research paper. Generally, whatever we do the research paper, we have to publish in the journals, scientific journals. Nowadays, everything is online. It is very easy for us to to correct it to the different countries or different scientists and all. It is very easy for us. In those days, we have to look at the printed media and all. Now, so this was he got the Nobel Prize, and he got connected with Davis and German. There experimentally he proved that light has dual nature. How it is? Example, suppose if it has, so he says that every particle, the concept was every particle is associated with a wave. Are you understanding, all of you? Yes.
Yes, sir.
Yes,
Okay.
sir.
Now, he says that every particle is associated with a wave, and that that wave has a wavelength. What is that wavelength? Is lambda. Lambda is equal to h by b, which is equal to h by mv, which is equal to h by under root of 2 mev, which is equal to h by under root of 2 m capital E. So there are total 5 formulas. I put it in one equation. Okay. So lambda, every particle is associated with a wave. Suppose a particle is electron is moving in the space, it creates a wave. It develops, it produces a wave. Okay, it produces a wave. Okay. Now, is there any other meeting going on now parallel to this? Yeah.
No, sir.
Oh,
No, sir.
okay.
Nothing.
So now what happens is every particle is associated with a wave. Okay, and that particle has a wavelength lambda. Lambda is equal to what? H by b, which is equal to h by mv. H is Planck's constant, and h by under root of 2 me. We have the relation between momentum and energy. Yeah, so we can write here. Are you able to see this? H under root of 2 m e capital E. Is that clear now? So h by under root of 2m capital, or h is equal to also h by under root of 2m, which is equal to 1.22 by root v 1.22 by root v nanometer. Okay, this is only for electron. This is only for electron. Like that we have for proton also. Means now see what is, from where we got this one? We have v is equal to w by q. Remember, v is equal to w by q, and w is equal to bq. So here 2me in the place of E, can we write W is equal to VQ in the place of E? E is work done or energy. They have the same dimensions. Can we write like this? So it becomes E into V. Is that clear? Is it clear?
Yes, sir.
Yes, sir.
So that will become 1.22 by root V nanometer. So we have two types of particles. One is C. If it is only particle nature, so this is the formula you have to remember. Definitely one question is going to come. It won't be that direct. They will say the wavelength of proton to alpha particle. The wavelength of proton to alpha particle is 1:4 ratio, or 1 is to some ratio. Then they will ask you to find out maybe something else, maybe the energy, or maybe the voltage or something. They will ask like that. Got it? It won't be a direct question. Every year he's asking a question. Without this, you cannot think in question paper. So this is this formula is very important. Okay. So please do take a note of this. So this nanometer, 1 nanometer means how much? 10 to the power of -9 meter, or 10 to the power of -6 meter. Then if it is only a particle nature, we would have got dots on the screen, right? On the photographic plate. Is it not? You understood now? Suppose if you have, if you have only dots, you should get only dots, so many dots on the photographic plate. Means if it is particle nature of light. If it is wave nature of light, we should get like patterns like this, like fringes. Have you seen in the interference pattern and diffraction pattern? Right, you have seen that, right? In interference pattern, you got lines like that, is it not?
Yes, sir.
Yeah,
Yes, sir.
you remember in interference we had continuous bright and dark fringes. So
Yes,
if it is wave nature, you will get this type of lines. If it is particle nature, you get only dots. So it had dual nature. Dual nature means it has patterns like this. Means in each and every line, there will be, again, he took the microscope. He took the film, the photographic plate, and he took the microscope and magnified on each and every line. Then he saw so many dots very close to each other. This is missing in the textbook actually. This thing he did not explain in the book. This is from some other book I am explaining you. But this is actually, students don't know. They stop here. But they don't know what exactly, why the name was given dual nature. Got it? This is a practical evidence actually. German, Davis and German, what they have done actually. Thing is, like there are, like this is, if it is only particle nature, it will be like this. If it is only wave nature, it will be only fine lines. But if it is dual nature, what he did for each and every line, he took the microscope and magnified that one. Then he saw so many particles in each and every line. Got it now? They are very close to each other. Is that clear?
Yes, sir. Got
So
it.
what we say is like pixels, pixels. I don't know, not good at that one, but like pixels of light, on the screen
Yes,
and
sir.
all. Such thing. Okay. So now, generally it is measured in wavelength is measured in nanometer and micrometer. Nanometer means 10 to the power of minus 9 meter. Micrometer means 10 to the power of minus 6 meter. Keep this in the mind. Now, so this is what he has explained. Okay, please note down this one. Then quickly we'll go to the second and third topic. Okay, two more topics are left. Small topics. Okay, so we can stop. We can finish off this and we can start new lesson, that is atomic structure. Okay.
Yes, sir.
Okay. Any doubt in this, sir? Suhas, Arjun, Vishnu, and
No, sir. Nothing,
yeah.
sir.
Please keep writing
No, sir.
messages in the group, okay, to join the class. Otherwise, they will be sleeping.
Sir, that while you're extrapolating that with your graphs
Uh,
are over there, isn't this one going into negative? Isn't the frequency going to negative?
yeah, it is going in negative. No. Frequency is not going negative. This is zero. Okay, got it.
Yes, sir.
Maybe I'm not saying frequency is negative, but maybe it is in infrared region. This is ultraviolet region. Got it. This much is visible.
Okay. Yes, sir.
This much is visible. Maybe this is infrared and this is UV. It works in that way. Okay. Yeah.
Yes, sir. Okay, got it.
If you have any doubts, please ask me. Yeah, are you done with this? Finish?
Yes, sir.
See, in this topic, photoelectric effect or and wave theory of light is deleted. That small topic is deleted. And there are certain features. Okay. So four definitions anyways are there. So that you have to learn. That is, one is photoelectric effect, stopping potential. Then, you know, what is that? Threshold frequency. Those four definitions you have to learn. And the features of photoelectric effect. He says that it is an instantaneous process. Photoelectric effect is an instantaneous process. Means when the light incidents on the metallic surface, immediately the electron will be released. That is, the time difference is 10 to lag is 10 to the power of minus 9 seconds. It's very small. Okay, 10 to the power of minus 9 seconds. Now, so shall I start now? Go to the next topic.
Yes, sir.
Okay. So we'll start with the next topic, that is Einstein's photoelectric equation. So here we have Einstein's photoelectric equation. Tomorrow, what is the exam? Energy
Maths.
mathematics. Okay. Energy of energy quantum of radiation. Energy quantum of radiation. Okay. So here we have Einstein's photoelectric equation. That is energy quantum of radiation. So Albert Einstein, he supported. So as I told you, Albert Einstein, he published three papers in 1905. Then, so in 1905, he published that paper. What is that? Photoelectric effect. So then, he said that light travels in the form of particles. Okay, that is known as photons or quanta. Light travels in the form of quanta. So he says that light travels in the form of quanta. Particle, that is quanta. Photon is a particle. So this is a quanta in the form of quanta. In the form of particles called quanta. They are particle nature. So they are particle nature. Now, so what happens when light incidents here? So when light incidents here, so electron will be ejected out. So this is what h nu. This is the energy of the incident radiation, and this is the kinetic energy, and this one is what phi. What is phi? Phi is the
Work function.
Work function. Okay. So he says that h nu is equal to what? Phi plus half mv square or k max. Is that clear? Phi plus half mv square or k max. Now we know that generally if h nu is greater than photoelectric, that electron emission will take place. If example we have if h nu is greater than phi 0, there is work function. H nu is greater than phi 0. What will happen? Photo emission takes place. Photoelectrons are emitted. Photoelectrons are emitted. Okay, if it is greater, photoelectrons are emitted. Photoelectrons are emitted. Now, so what happens here? We also know that phi 0, that is h nu is equal to phi 0. Okay, h nu is equal to h nu 0 is equal to phi 0. So we will equate both of them. Is it clear? So we will equate both of them. So what will happen now? H nu is greater than h nu 0. So this and this will go away. Implies nu is greater than nu 0. Is that clear? Nu is greater than nu 0. So we have what is the formula now? Nu 0 is equal to phi 0 by h. Nu 0 is equal to phi 0 divided by h. This is the formula for threshold, the work function. The next formula is what? This is the first one. The second, so this is the actual formula. Okay. Now, he writes the same formula as h nu is equal to what? H nu is equal to phi 0 plus E into V0. Because maximum kinetic energy he is writing as E into V0. From where we got formula W is equal to VQ, and from there we got this formula. Okay. So maximum kinetic energy is E into V0. Now, if you simplify this one, so what will happen? Implies E into V0 is equal to what? H nu minus phi 0. So what is V0? V0 is equal to what? H into nu by E minus phi 0 by. As I told you, it is in the form of y is equal to mx plus c. So if you see here, m is equal to what? M is the slope, is it not? M is the slope and c is the y intercept, is it not? Is it clear? So m is the slope and c is the y intercept. Okay, so what is the slope value now? Slope value m is equal to what? H by E, and slope intercept is minus phi 0 by E. Okay, so this is the formula. So we have V0 is equal to what? H by E into nu minus phi 0 by E. So how did we find out the Planck's constant here? See, as I told you, the stopping potential versus the frequency of incident radiation. So what happens? This is meeting at a particular point. This is C. Is that clear? So that is why we got negative here. The y-intercept value is negative. Is that clear? Is that clear? From this is
Yes,
the
sir.
Yes, sir.
significance of, yeah.
Yes, sir. Got it, sir.
Got it? Understood? So once again from the beginning. So Einstein's photoelectric equation. And Einstein's in Einstein's photoelectric equation. So okay, so in Einstein's photoelectric equation, what we have now. So Albert Einstein in 1905 he gave the experimental study of photoelectric effect. So he says that light travels in the form of particles. That is called quantum. Okay, after the later on named as photons. Quantum is discrete energy packets. Okay, when I say quantum, it is discrete energy packets. Discrete energy packets. Okay. So now, what happens when light incidents on a surface? Electrons are ejected out. So this is the work function. So h nu is equal to phi 0 plus k max. If h nu is greater than phi 0, then that means what? We also know that the work function is equal to h nu 0. That means this is a threshold frequency. So this is equal to what? H nu is greater than h nu 0. H and h will get cancelled. Nu is greater than nu 0. Nu 0 is equal to phi 0 by h. Now we just substitute in this formula again because maximum kinetic energy is E into V0. What is V0? Threshold, the stopping potential. Now simplify that equation, bring in the form of y is equal to mx plus c. Then we get y is equal to mx plus c. Then we get the equation in this way. So what did we get now? This equation has long significance. Why? Because from this equation we found out the Planck's constant. Is that clear? We found out the Planck's constant from this formula. There is no, I am telling you again, there is no derivation here in this lesson. Only the equation. See that of see photoelectric equation only. Means what is h nu here? I'll write here. H nu is energy of incident ray. Energy of incident radiation. H nu is energy of incident radiation. Okay. Then second one is what? Second one is phi 0. Phi 0 is work function. Phi 0 is work function. Third one is, this is K max. Maximum kinetic energy. Maximum kinetic energy. Okay. And what is nu? Nu 0 is threshold frequency. Nu 0 is threshold frequency. And V0 is stopping potential. Stopping potential. And the last one, what is that? That is H is Planck's constant. H is Planck's constant. The value of Planck's constant is how much? 6.624 into 10 to the power of minus 34 joule second. Okay. 6.624 into 10 to the power of minus 34 joule second. Just copy this one. Then we'll quickly go to the last topic of this lesson. That is particle nature of light, photons. Okay. That only 5 points are there that we will write and we'll stop the topic and we can start a new lesson. Any doubt in this one, please ask me.
No, sir.
Yeah.